So this is a very fun topic for me to teach. It's a nice culmination of all the things that we've learned in this class, because the goal of CSCI 41 is not to go one day program a heap. Maybe you will, I don't know, it depends on what you're doing. But usually you'll just use library versions of all the data structures that we've learned in this class. You know them well now, you know when to reach for them. And kind of how you deal with knowing that, having that knowledge in your brain is when you have a problem that your boss gives you or something, you're going to have to learn how to combine the data structures that you know to solve the problem. You don't have to reinvent the data structures, but you have to use them in the right way to get what you need done. So that is that's kind of the moral of CSCI 41. And so this is a great topic. It's about compressing some data into smaller data. So if you have a zip file, for example, that's compression at work. We're going to talk about one form of compression, images are compressed. They're not accurate, especially the JPEGs, right? We'll talk a little bit about one form of compression, how to make a file smaller but still keep everything that's there. So that'll be fun, and it's going to combine a bunch of data structures, which is great. So that's a wonderful, wonderful thing. So let's learn about files and compression first, and then I'll teach you the algorithm. It's called Huffman compression. All right. So first of all, why in the world would we want to make a file smaller? I think you can probably think of some reasons, right? You have a big long string, right? Let's make this concrete. You've got a big long string, because what is a file but a string of text or bytes in the worst case, right? Random bytes. And you want a smaller version of it. That would be nice for a number of reasons. You wanna send it to somebody else's computer, and you don't want them to have to wait so long, right? Because maybe the internet connection is slow. Their computers are fast. They can decompress it quickly. That's fine. Maybe you want to put this thing on some small embedded device, like a pacemaker, a really tiny, tiny chip that lives within your microwave or something, where you don't have a lot of space, but you want to store a bunch of stuff. Like a very small video game, for example, like Game Boy games, they had to deal with this kind of problem. They had to invent their own compression algorithms. And then what if you want to store high-definition video that is you can actually watch? Because just think about it. HD video, right, is 1920 by 1080, right? So think about how many pixels are involved. 1920 by 1080. Let's do some math. 1920 by 1080 per frame of the image, right? So it's that many pixels. Let's pretend that each pixel is a byte. That'll make it easy for us. And you want probably, what are the movies? It's 23 point something frames, 24 frames per second, right? And maybe you want just a minute long video, right? If you were to store that uncompressed, you'd need that many bytes of data. We divide that by 1 billion-ish. That'll give us gigabytes. That's already 3 gigabytes per second. That's disgusting, right? So there's got to be a better way, so that we have to do something to that. There's ways to compress videos, of course, to make it maybe a megabyte to have that kind of quality, but maybe you've lost a little bit of information. That's called lossy compression, by the way. JPEG is an image format, and pretty much every video format is compressing data. It's not actually keeping the original frames of either the image or the movie. But to your eyes, it kind of tricks it into thinking that it looks fine. So that's called lossy compression. We're not going to talk about that today. That's more advanced. We're going to talk about lossless compression, where we are keeping the original data intact. Lossless compression. Boop. We're going to keep all the data intact. And so the goal then is we've got a large file. We'd like to compress it so that we can send it across the network or have it be streamed to a user's device. Compression. To make the file nice and small and bite-sized. And then we'd like to be able to decompress it, decompression, back into the exact same original file. It's not lost anything. We haven't changed some pixels around. That's lossless compression. We get the original file back with no issues. Okay? So that's useful if you want to compress a book or something, like a story. You don't want to change the words around. You want to keep it the same. So compress it and then get it back to how it was. So that's kind of what actually happens when you go to any web page. All the web servers are serving you a compressed version of that web page, and your browser is decompressing it. So it saves network bandwidth. So, all right, a good example is like, let's do English text. So like, say you are going to compress a book or something. We know that some letters are more important than others in the English language, right? Our vowels are very, very important. They appear so very often, right? So if you take this exact sentence from that bullet, I've counted, there's 4 A's, 5 E's, 1 I, 6 O's, and 1 U. That is 30% of this data is vowels only. See that? So if we could maybe compress the vowels, right? Because ASCII text, right? ASCII text, this, let's say you got 26 letters in the English alphabet. Let's pretend we're not capitalizing anything. Forget about spaces. The vowels, there's only 5 of those, right? Only 5 of those, but they have a lot of importance. They're 30% important, something like that. So if only we could encode our data, because all the ASCII values, they're a byte long per character. If only we could encode our characters so that like A, E, I, O, and U are tiny, and like letters that you don't use as often, we can have a trade-off there. Or like let Z be several bytes long, because we'll barely ever want to use a Z. Let Q be several bytes long, at the expense of making the vowels like a couple bits or something. Does that kind of make sense? That would work. That's an idea. So like, what's the best way to do that is now the question. I'll show you an algorithm that can be provably the best way to do that. So that's really cool. So yeah, if we could do something like this, if we could change the representation, like such a small amount of data, like so few characters are just so important, we'd like to represent them with maybe just a few bits rather than the full byte that they are in ASCII charland. And then we could change like letters we barely use to have more bytes maybe. And I think that would be a good trade-off, and we'd still get a space savings. Okay, something like that. Let's encode it differently. That's kind of the goal for today. And the way to get there is a new kind of data structure that is pretty much a tree. It is, oh goodness, this is disgusting. I'm sorry. So we're gonna learn about a data structure spelled like this, and it comes from the word retrieval, but we pronounce this data structure as trie. They are tries that we're going to learn about. All right, it's weird. Sorry. The reason we do that is so that we don't confuse it with trees, because it is a special kind of tree. All right, so tries, try by itself like that. What they hold at the end of them is strings. They help you build up strings. It's a good way to like store a dictionary, for example. I'll show you some diagrams on the next page. But when you have a trie, you're encoding text, usually. You're encoding words, maybe strings. And the operations on your trie data structure are search, usually. You want to go look and see if the thing's in the dictionary, that the trie represents a dictionary. And like insert a new word into our dictionary. Something like that. Let's see if it's in there. All right. So here are 2 drawings of a trie. And for some weird reason, why did it want to scroll up like that? I don't know. It's fine. So here are 2 examples of tries. They are just trees with usually more than 2 children, an arbitrary number of children, as many as you need. But what's going to happen is each edge in a trie, each edge that you can follow, like that guy, that guy, that guy, those are edges, right? Each edge is a character. So this is a nice compact way to save like a dictionary, like for autocorrection or something, autocompletion, because like here are some words that you could have in a trie. So the root node just means you haven't used, like it's empty string, haven't seen any characters yet. But if you follow the T and then the O, you get to a leaf, and that is the word to. Like that's us encoding the fact that the word to is in our dictionary, T-O. And then, of course, from T, you could have branched off and gone to E, right? TE is not a word yet, but TEA is a word, TED is a word, TEN is a word. You see how we're encoding that? You could save words in there. All right, so the characters on a path, along a path down to usually a leaf, they build up words. All right, so the characters along a path build upwards. And usually it's the leaf. You stop at a leaf when like that's a word. You're done yet. But there are also some of the intermediate nodes, right? The internal nodes. Sometimes those are also words, like in and in. Those are both words in the dictionary, right? So we should also, like, one builds the other. We should also like have a little marker maybe on in to represent the fact, like, oh yeah, that's an actual word. That's not just a piece of a word. Whereas te, I don't think that's actually a word. Like that's not done yet. But this one, this internal node, that is an actual word, so we can mark which intermediate nodes are words if we want to. That's the thing. So yeah, the characters along a path build up words, and if you had this data structure for every word in the English language, it would be very quick for a computer to spell check, like your text message or something. Does that make sense? You just like follow when you press space, all right, we're back at the root node, and then like you're typing out stuff, and if you ended up on a word that's been marked or if you end up on a node that's been marked as a word, like you're good. But if you press space after you ended up on a word on like an intermediate node or something, or you went off to somewhere like you did TOZ or something that's not existing, then you would like get a red underline. That would be a very quick and efficient way to mark whether your words were spelled correctly. And so that's as good as you can do. That's linear time, right? That's beautiful. Can't do any better. So okay, and here's another example where you have definitely intermediate nodes. Like, and root node means you haven't done anything yet. This time they're putting letters on the actual nodes, which is fine too. It's like bat, that's a word. Ball, that's a word, right? Do is an intermediate node. That's totally a word. Then doll, do, dork, dorm, yeah, all those things. Okay. So do you see how you can encode words using this trie data structure, where the edges or the nodes, they hold characters, and you can build up words along the way. Or anything you want to put here. Just like we're thinking of it as text, but you don't have to put text there. All right. We are going to study, for compression purposes, a binary trie, where you can only go left or go right, and it's a 0 or a 1. You're building up a string of bits, zeros and ones only, all right? So a binary trie is when you only have two different kinds of edges. It's always 0 or 1. Edges are 0 and 1. And what do you know? That's just a binary tree, but we call it a binary trie because it's building up strings of ones and zeros. So like if you went left from here, right? That would just be like 0 is the left edge, 1 is the right. So like you just made the string 0 there, right? If you went right, it was 1, 0. If you went 1, 1, left 0, 1, 1, 1, that's 1, 1, 1. Does that make sense? Like you're building up a binary string now. That's fine. And what we'll do is we will represent actual characters using the path that we took. Like those are the bits that are going to represent a certain character, the path that we took to get to that character. So what we're going to do is we're going to put letters on the leaves of a binary trie, and the way that we got there is going to be the encoding of those letters. That's what we're going to do, and that's how compression is going to work. All right. So like the goal is like, oh, we know that A is a very popular character. Let's make it be represented with just the number, like just one single bit 0, because that's an 1/8 of the size of a normal A character. And that's beautiful. So let's make it have the smallest possible bit string of bits to represent it. So A is a popular character. All right. And so it's encoded. We're going to encode it with a small bit string. Just 0. Just the bit 0 is going to represent. Every character is going to be represented by a bit string. That's how this is going to work. Okay? So that gives us a compressed encoding of characters. And what I mean by that is normally when you have a single char, right, you may say char C or something, that saves away, that takes up 8 bits in memory. It's a single byte, right? 8 bits is 1 byte, which is equivalent to 1 byte. Those are all equivalent ideas. Equivalent amounts of space, at least. And if we say like, hey, no, it's not going to be a byte anymore, it's going to be a single bit. Like we've made it an 1/8 of its size. Does that make sense? And that saves some space. That's quite nice. If you only want to represent 26 characters, if it's just that and maybe a space character, then you should probably not be using the char type. That would be make up your own. Okay, so we're going to represent a compressed encoding of characters in this way, where we've come up with this binary try somehow in some fancy way to encode like more important characters like A being very short bit strings, and like less useful characters, less ones that appear as often, like D maybe is not as often, it doesn't appear as often as A. Like we'll encode that with 111, that's 3 bits. It's still a savings of 5 bits, right, over the normal char encoding, but it's a bit longer. So that's the trade-off. And so, like, for example, if this was our binary try, we're only going to represent the characters A, B, C, and D. There's a binary try that does it. If we wanted to store the string ba, right, B-A-A, that would be 1, 0, right, to get to the B. It would be 0 to get to the A, and another 0 for another A. Does that make sense? So I've just stored 3 characters in half a byte. That's quite nice. That is compressed, yes? That's pretty cool. So does that make sense how I'm reading that try, that binary try, and getting out, like, ba would be encoded in that way? Is that clear to us? Any questions about that? All right, your turn then. So here's the same one. Using that binary try, please create the compressed binary version of this string, BAAA DCD. All right? So go through that, write it down. Maybe you can use the written nice page. How about we do that? So just as a group, you guys can hang out and see what you're thinking. Agree on an encoding. See if you get it. And then write down how many bits was it compressed. This is the compressed version of DCD. And uncompressed, remember, it is going to be the length of the string times 8, because every character, one character, is 8 bits. It's 1 byte. Every one character is 1 byte, which is 8 bits. So that's the original. Like if you store it as an array of characters like it would be in C++, it would have taken up that much space. How much space did we save? What's the difference? So I could do the encoding, figure out how many bits it was, and then calculate how many bits it was uncompressed just as an array of characters. Make sense? All right, give that a try for a few minutes. Hopefully you'll agree that this is a really, really cool thing to be doing once you see the savings we get. I guess you can just read off the bottom, but like understand how to maneuver around the tree as well. And by tree, I mean try. Special kind of binary tree. All right, was that enough time? We're not really talking too much, so was it just so easy? We can see it. Did we get some stuff down? A few of us, at least. Think about it for another few seconds, then. But this is going to be the topic of your last and final lab in the class. So you got to be able to read these tries. Otherwise you are doomed. All right. There we go. Yeah, we think 1456. Nice. That seems to be right. All right. Let's do it together. Okay, so B is 1, 0. Boop. A is just 0. So we got 3 of those. 0, 0, 0, right? D is 1, 1, 1 to get to the D node. 1, 1, 1. C is 1, 1, 0. And D again is another 1, 1, 1. So how much is that? 3, 6, 9, 10, 11, 12, 13, 14 bits. And in terms of bytes, that's like 2 bytes is 16 bits, right? So it's less than 2 bytes, which is wonderful. Whereas how many characters are in here? 1, 2, 3, 4, 5, 6, 7 characters. It would have been 7 bytes to store it. And we really compressed it then into under half its size, under a quarter of its size, maybe. I have to do the math, but 7 times 8 number of bits. That's how many we're using to encode the original string if you just did an array of characters. 56 bits, right? That is a lot, I think. Yeah, there we go. Any questions about that? Do you see the savings? You see how nice that is? That's wonderful. So good. If only we could generate a try like this, that's like the optimal one for the text we would like to compress. That's the goal. And so if you agree with me that that is a good goal, here's the algorithm. This gives you an optimal try encoding for bit strings of every character that's going to appear in a file you care about compressing. It's called Huffman coding. It was invented by a dude with the last name Huffman. And yeah, here's the trick. You're going to use a binary try. You're going to generate a binary try by using a heap. You're going to prioritize more popular characters, and then eventually more popular nodes in the try is going to get weird and cool. It's a great combination of some things that we know. So yeah, everybody, of course, I just taught you that this is called a binary try, but when you do Huffman coding and you generate that binary try, everybody calls it a Huffman tree. I'm so sorry. So you can interchange the word, nobody will get mad at you. So, okay, our goal. What we want to do is we want to take like the text of Shakespeare or something, and we would like to make it smaller. We'd like to make a smaller version of that same file where we take the characters that appear and how often they appeared, and like probably the A is important. Give that a small bit string implementation. Give that a small bit string encoding. So shrink the amount of information needed to take that text and make it whole. All right. It's like you can transmit the try as well as the text, and like that's going to be much, much shorter than the whole uncompressed thing, okay? Because normally, remember that every character is 8 bits, that's a whole byte, but we know from experience that several characters are more popular than other characters, and so we should use smaller representations of the more frequent characters, because then when they appear so often, they will take up fractions of the space that they normally did, right? Fewer bits total. And so if we do that at the expense of maybe making some non-frequent characters take up more space, we'd still get an overall shrinkage of a decent amount. All right, so the overall file size is most likely going to shrink for sure. And yeah, there's an algorithm due to this Huffman person that gives us this ability. We're generating the try using a priority queue. So we're combining like trees and heaps, essentially, to do something cool. So yeah, are we ready for the algorithm? I'm excited. So here it is. Here's the algorithm. I'm going to say these words, and I'm going to give an example. All right, I promise. So let me say the words first. You do it in stages. The very first thing you need to do is go through the entire file that you're trying to compress. Go through everything, every piece of it, and count how many of each character there are. Count every character you see. Count how many lowercase a's there are. Count how many capital A's there are. Count how many lowercase b's, capital B's, spaces, semicolons, whatever you need. Everything that appears, count however many times every single character appears in your file. Every single one. All right? Because then you know which ones are the most important. You need that. You need that knowledge because some of, I don't know, if you're compressing like a Polish text, they like to use their Z. That's a very popular character for them. So, like, it depends on what you're trying to compress, which character is the most popular, yeah? So, go through the actual text you're trying to compress. That's what you want to shrink down, all right? And then we're going to build a Huffman tree, which is really just a binary tree, from this frequency table, all right? And that's going to make sure that the characters, because it's always going to look like this, the tries, the Huffman trees that we're making, they're always going to look like this with the characters at the leaves, and going left versus going right meant adding a 0 or a 1. All right, so the characters at the leaves, they're going to like take up less space. The more frequent ones, they're going to be easier to get to, quicker to get to from the root node. All right, that's how that's going to work. So yeah, ensuring that the characters stored at the leaves that are used more often have shorter codes, which is their encoding, right? The paths to them, the binary encoding of that is going to take up less space. All right, that's the goal. And so, yeah, the way we're going to get there is we're going to use a priority queue ordered by, it's going to be a min queue, right? Min priority queue of, oh, sorry, excuse me. No, it's going to be, yeah, actually it is. Sorry, a min queue, yeah. Min priority queue of frequencies. We're going to start with the least frequent things. We're going to start kind of opposite, backwards. And that lets us add the most frequent ones last, which makes a shorter path. That's how it's going to work out. Okay, so we're going to start with the least frequent things. We merge them together. So we're going to prioritize. We're going to make a priority queue, not of like characters and their frequencies, but of like eventual nodes in this trie, and also subtrees. Like we can add this whole thing as a piece of our priority queue if we get to it that way, and we are. So look forward to that. So we're going to add subtrees, starting with the leaves. We're going to build up subtrees, and that's what we're going to order in our priority queue, all right? Starting with the least frequent ones, and if we ever merge two things, we're going to say that the frequency of like the A and the C character subtree is going to be their combined frequency, how often the A character and the C character both appeared. So that's what's going to happen. We're going to combine their frequencies if we ever make a subtree and add it back into the priority queue, because it's a priority queue of nodes. And yeah, just until the end of time, until there's nothing left, until we've combined everything. There's only one thing, that is the final tree. Keep on taking two nodes, popping off two nodes of your priority queue, two subtrees with the smallest frequency, and then attach them together. The new frequency of that combined node is the sum of the inner frequencies. All right? I've said the words, now we can give examples. All right, but the second you've done that, the second you pop the last two, combine them back, now you've just got one big one big tree, you push it back into the queue, I guess, if you're not sure if you're done yet. Like the second your priority queue has one thing in it, that is the entire Huffman tree. All right. So I've said the words. I don't expect them to make a lot of sense. Are we ready for an example of those words? All right. A drawing speaks 1,000 words. So here, I made these slides during the pandemic, and so we get to use this nostalgic game as an example. All right. So here is the string we would like to compress. Let's forget about space characters. Let's say we want to compress the string emergency meeting. All right. And so here is the frequency table for that text. E is by far the most popular character. And then you got some M's, some G's, some N's, and then everybody else is just frequency 1. But that's the frequency table. You go through the entire text. Probably should be counting the fact that there's one space. But I'm going to, just for ease of use, we're going to not care about that right now. That's the frequency table. Does that make enough sense? Like, keep track. It's like you can make a hash table or something where the chars are the keys and the ints are the values. Yeah, something like that. So, yeah, there's the frequency table. And the next step is we're going to make a priority queue, and we're going to make every character a leaf. Like all the leaves, we're going to start out with these leaf nodes. Like A had, I don't know, four times in the frequency table. B had 3 things in the frequency table. C had frequency 2, D had frequency 1. We're going to make those nodes. Every node is going to have a left child, a right child, a character, and a frequency. All right? At least every leaf is. Internal nodes don't need a character. Only leaves have characters. But that's what we do first. We're going to make every character into a leaf node and attach the frequency to them. And then we're going to push those onto the priority queue ordered by, it's going to be a min priority queue ordered by the frequencies. Okay? So here on the next slide, here's our priority queue. All right, and I'll let you try some of these in a second. But our priority queue, PQ, I guess, it starts out being all of these nodes. All of these nodes are all going to be pushed to the priority queue in this way. It's like we're going to have an E node with frequency 5, an M node with frequency 2, an R node with frequency 1. We're going to add all of those. Okay, so that is the very first step, and I guess we need to make that happen. So I'm going to push every character to our priority queue. All right, and I'll stop you and I'll ask stuff, I guess, eventually. But like, all right, here's our priority queue. We've got E having frequency 5. That is a node in our priority queue. We're going to make a leaf node, no left, no right. That's it. Push that. Push the node itself, or a pointer to it on the heap or something. Do that. We're going to do, let's see, is that what I want? I guess I'm stuck. Let me check my notes real quick. Do I have to do that? Okay, good. I was worried about something. Never mind. I'm going insane. So, okay. Then M is 2. That's another node. We're pushing that onto the priority queue ordered by, it's a min priority queue ordered by the size, or sorry, the frequency of our nodes. The size of the amount of characters we saw for that character. So R was 1. Add that node. Oops. That's in our priority queue. G was 2. I'll just do this quick now. G was 2. N was 1. Boop. That doesn't look like a G to me for some reason. Then C was 1. And then Y was 1. And then T was 1. And then I was 1. I think that's everybody, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Looks about right. So that's my priority queue. I'm going to push the nodes themselves, or pointers to them, into my priority queue, and I'm going to be prioritizing smaller frequencies. All right. So the first two things, like the next step of this is we want to keep on building up our Huffman tree, by taking the 2 least frequent nodes and combining them into like a mega node, a bigger node that contains both of them and their combined frequency. All right, and that's going to be a subtree at that point, and we're going to push that new subtree back into the priority queue, and we're just going to keep doing that until we only have 1 node left in the priority queue. That's the game we're going to play. All right, so I have this priority queue. It's a min queue, min heap ordered by preferring smaller frequencies. And so if I need to pop this twice and combine 2 things, because that's the algorithm, I need to pop this twice and combine 2 things, it's just kind of which of the 2, right? They're all the ones, right? Those are the smallest ones, yes? And so I guess it's arbitrary which of the 2 we pop first. You would have some sort of tiebreaker probably, but let's just, for the sake of example, say that we're going to combine the T and the I first, all right? Let's say that T and I get combined, and so how it works is we pop them off for a split second, and then we combine them and we push them back into the combined node, back into the priority queue, all right? So take these 2 off, then we fuse them together by making a root node between them, just like this. Boop. And then the frequency of this new subtree that has the both of them, the 2 of them, it's going to be their combined frequency. So that was 1, that was 1. So the frequency of this the super node that contains them both, we'll say is 2. Does that process make sense? We're just going to keep doing that, all right? Just going to keep doing that. And it was also arbitrary which side I put those on, because there was no difference. They're both 1s. Didn't matter. It's honestly not going to matter at all either way. So yeah, we're just going to keep playing that game now. So this now, it goes back into the priority queue. This is now the whole priority queue. And it has, like the frequency of this bigger node is now 2. So we're not going to pop that node off next, are we? When we play this game again, we take 2 things. So it's always going to be take two things, repeatedly take the two least frequent nodes, breaking ties if necessary, and combining them into like a supernode that contains the two things, and their combined frequency is what goes at the root that combines them. All right? So I hope you can see that, all right, we still have some ones, so among these, we're going to pop two of those. Yeah, those are going to be the next ones that go. So I'll just break ties arbitrarily. The C and the Y, they're already next to each other, so I'll combine the C and the Y. Okay. So I'll bring those over here, and so I'll pop them off and I'll combine them, and I'll add the combined node back into the tree with frequency 2. See that? Does that make sense? All right. So that's how that works. And then same with, you can imagine, let's see what else is going to take place here. R was 1, N was, oh sorry, N here was supposed to be 2. I wrote a 1 accidentally. Let me fix that. There we go. So now we get to do it again, right? We're going to repeatedly take the two least frequent nodes and combine them. So who's going to be popped now for sure? R is going to be popped, and then the rest is now, it's a game among the twos. Yeah? So it's arbitrary which ones you pop. It doesn't matter. This has frequency 2, that has frequency 2, that. It doesn't matter. It's still going to be optimal. But just for ease of drawing the tree, let's just say I'll take the R and put it next to, I guess in my example, I did the N for fun. So those are the two. I'm going to pop the R for sure, and then one of the two nodes with frequency 2. Breaking ties arbitrarily. Oops. And I will break ties and say that the N's coming. And it doesn't matter which side of these I put them on. I'm just going to follow what I did in my notes. I'll put the R on the left and the N on the right. Did not matter though. Which side? And then I combine them, and their combined frequency in the priority queue is going to be 3. See it? See the game we're playing here? So, all right, you better believe that we're going to pop, for the next time, two things with frequency 2, because that's the minimum right now, right? 2, 2. We could be popping that one or that one. Like those are fair game to be popped off. But this is the whole priority queue now. Is the process still making sense? So that's the algorithm. Of course, you have to code this up. Like you're pushing and popping, I guess, Huffman tree node stars or whatever. Like they represent subtrees. And then, yeah, let's pop a couple of them next. So the two least frequent nodes, and we combine them. All right. Well, let's do, I guess just for ease of use, I could be like popping this guy and that guy and combining them, but just to make the tree easiest to draw, I'll do the M and the G, yeah? It doesn't matter which ones, though. It's still optimal. Boop. Boop. So I'll combine those two into a supernode that is of frequency 4, right? There's some frequencies. So, all right. We're getting there. See how the E has not been chosen yet? The E was the most popular one. It's not been chosen. It's not been put into any subtree yet. And that's going to make all the difference. This is why this is optimal. So that's going to look really cool soon. So, all right. Who are the two, like, we have really 5 things in the tree right now, right? This guy, this guy, this guy, this guy, this guy. They're all whole together. There's only 5 things, 5 subtrees in our heap, in our priority queue. So, who's going to be popped next? Which frequencies? The 2s, right? This guy is going to be popped, and this guy's going to be popped. And we can put them on either side of each other, I guess. That's funny. Get out of there. So let's pop these guys, and for fun, I'm going to put the TI on the right of the CY. It doesn't matter which one you did, but I'm just going to follow what I did in my practice notes. The order did not matter. So that's going to be my combined node, and what should be the frequency of that combined node that's going to take both of these together? 4, right? So really it's combining the frequencies of the leaves, but you can just look at the nodes you're combining because they're always summing up what they had inside of them. So that's going to be frequency 4. And so now the 2 things I'm going to pop, because you see every round the priority queue gets 1 smaller. The size of it gets 1 smaller. Eventually it's going to only have 1 thing left in it, and that will be the final Huffman tree. So all right, then we have 3 to pop, and then it's either this 4 or this 4. It is easier for me to draw and combine it with that 4. So that's the one I'm going to choose arbitrarily, all right? Just for my own sake. Didn't have to be that one, though. Could have combined it with this one. I'm going to get it out of the way for a second, though. So let's do it with, I don't know, put the 3 on the left, the 4 on the right. Did not matter, though. Boop, just like that. And the combined frequency will be 7. All right. So we're getting to the end now. Have 3 things left. What will I pop next? 2 things. The 4 and the 5, right? Finally, the E is going to get some action. So I'll pop off the 4 and the 5 nodes. I'm going to have to make these smaller. Might as well do that now. Become small, please. Over there. Become small, please. Try to get them to be the same size as each other. There. All right, so I'm going to pop the 4 and the 5. So the 4 is going to be combined with the E node. I'll put it on the right this time. Doesn't matter. We'll try to get these on the same level as each other, though. Let's do that. And then, so I'm combining the 4 node, the 4 mega tree, with all those characters in it, and just the E, which was frequency 5, so important, in that way. And the combined frequency will be 9. Yes? Boop. Boop. Just like that. It will bother me if that circle is larger than the others. That's better. And so now, my hand has been forced, yes? The 2 things I'm going to pop are going to be the 2 things left in the priority queue. This subtree and this subtree, and I will fuse them together in some arbitrary order. I'll just put the 7 on the left for fun, all right? And that's going to be very difficult for me. That's how I did it in my practice example. So this is going to be our final thing that we put into the tree. We're going to combine the 7 node and the 9 node in this way. Just like that. And we will get one big node with frequency what? 16. And that's the algorithm. That's the algorithm. The second you have only one node left in the priority queue, you're done. Stop your loop, pop it out. That's the one. That's the final thing. All right? So this now is an optimal encoding for that sentence, for the text we were trying to encode, emergency meeting. Let me draw the paths, right? Because when you go left, that means 0 is part of the bit string encoding. 1 is on the right, right? 1 is part of the bit string encoding if you go right. 0, 1, 0, 1, 0, 1. So do you see how E is 1, 0? That's nice and short, right? That's very good. So E, our encoding of E is going to be boop, boop, 1, 0, right? Right, left. That is a quarter of its normal size, right? And then C, which was not as frequent, still gets some space savings because you didn't have a lot of characters to compress. So that's going to be 1, 1, 0, 0 for the C. Yeah. 1, 1, 0, 0. Space savings across the board, right? The lowest level is 4. It's like you got four bits. You're still saving half the space, right? So that's lovely and wonderful. Are there any questions about how we computed this? Some of these things I broke ties arbitrarily, like the I and the T, they could have been swapped. It wouldn't have mattered, right? Because they would have been the same number of bits, just a different encoding, yeah? Wouldn't have mattered. So there's that. And this is going to be optimal. This is wonderful. And so once you've made your Huffman tree, you kind of want to visit, you want to do a traversal, right, of every node, get to the leaves and build up, like, remember what bits got you the R, what bits got you the N. Does that make sense? Like you need some sort of inversion table, like not a frequency table, but like a conversion, a compression table. I don't know, something that gives you the bits to represent every character with, so that you can like read that off really quickly as you're iterating through the file and compressing it. So, that's the bulk of the story. Here is our result. And so the next step is going to be we want to extract the lookup table. Give me the whole lookup table, please, from this tree. Something like that. So the way you do it is you do a recursive traversal with some extra parameters to keep track of like what's part of this. So it's going to be a recursive algorithm that's going to remember the path that I've gone along the tree. When you go left, like you remember that I need to tack on a 0. When you go right along the tree and visit the nodes to the right, you're going to remember to tack on a 1 in the final bit string. We're going to make that as part of a parameter, as part of an argument. All right. So yeah, and once you hit a leaf, that's a base case, like output the string you've built up so far, and that's the character it was for that, okay? So let's do that. So here's kind of the recursive algorithm. It's like you start off your algorithm by calling on the root with the empty string. I think you can imagine that makes sense, right? Empty, you got no bit string yet at the root. There's no encoding for anything yet. You haven't saved 0 or 1 yet. You haven't tacked on anything. So empty string at the root. And then you're going to recurse left and right. You're going to call your extract the lookup table. When you go left, like on roots left, you're going to tack on to this parameter that's keeping track of your sub prefix so far, your substring so far. You're going to tack on a 0. So like when you call it on this node, you're going to have the prefix 0 saved away. Like you're going to add 0 to what you had before, which was the empty string. And then you go along and recursively traverse that path. When you go right, you take your empty string and tack on a 1. Like that's the prefix so far. Does that kind of make sense? How that algorithm's going to come out? And that's the trick. All right, so you got a 1 there. And then you're just going to keep doing that. And then when you're at this node, you're recursively traversing it and calculating the lookup table for everybody. When you go left, you take your original string and you tack on another 0. Like that's the prefix so far. Keep going though. You're not done yet. So this node is going to see 0, 0. The string 0, 0, that's the prefix of anything that could come from me. This one's going to see 0, 1 for the same reason. This one, it had a 1. If we went left, it's 1, 0, right? 1, 0. And then if I go right, it was 1, 1. And you just keep on playing that game, traversing left and right, until you get down to leaves. And then like once you hit like 0, 0, 0, right, you notice that it was a leaf. You can't go left or right anymore. Like that's a piece of your lookup table now. Go put that in there. Go put that in there that, oh gosh, where'd that go away? That R is going to be mapped to like save the fact that, all right, the character at that leaf node was R. The string that I built up so far was 0, 0, 0. Come on, PowerPoint. Was 0, 0, 0. And I'll just map then that R goes to 0, 0, 0. Go back. And that's going to happen for every node because you're going to visit every node. And keep track of the prefix that got you there. When you get to a leaf, the prefix is the encoding. Does that kind of make sense how that's going to work out? It's going to be recursive, so it is a little weird, but that is the trick. Okay, so yeah, with that, I think that's most of what I wanted to say. Yeah, so that's the algorithm. You build the frequency table, you build the Huffman tree, then you extract the encoding from the frequency table by recursively traversing you extract the encoding from the Huffman tree by recursively traversing it. And then you can go through the file, like every time you see an R, map it to that. Like go out, put in your binary file that, the 3 bits, 0, 0, 0. Something like that. All right? Any questions about that entire process? That's more or less it. That's the algorithm itself. So, yeah. My gift to you is for this last lab, this is what your last lab is going to be on. As a nice winter holidays gift to you, I will implement it right here in class for you. All right? So you can read off the code. You can, like, if you want to type really fast, go for it. Whatever you want to do, let me release your lab. I will, of course, not be giving you this code. I will not be pushing this code to GitHub and letting you see it. So you'll have to follow along if you miss something. But you'll have the recording. Okay? So lab 10 is here. If you go get the files, it looks like that. Let me release it for you to see everything else too. It will be due. That is not our class. Let's do it now. Right? It will be due the last week of class, so December 5th. That's our last lab. So that's lab 10. Dun, dun, dun. Here we go. So it's all about Huffman coding. It's going to involve some fun things. There's going to be we're going to represent a Huffman tree, right? with a couple different kinds of nodes. I hope you see that there's different kinds of nodes involved here. There's a leaf node that has characters, no children, frequencies, right? And then there's internal nodes that hold frequencies and children. You see the difference? Those are different kinds of nodes. Those should be different data structures. They're holding different things. They're attached to different things. So you better believe we're going to use inheritance. We're going to have a Huffman tree node type, and then a subclass is going to be an internal kind of node, and another subclass is going to be a leaf kind of node. Does that make sense? They need different things, but we still want to use them to maneuver around the tree. So we're going to have to put some stuff in the abstract base class to figure this all out. All right, but we're going to have two different kinds of nodes. I hope that makes sense. All right, and so there's a few parts to this file. There's the Huffman tree node stuff. There's our little subclasses. That's in huffmancoding.h. I'll show that to you in a second. There's a bunch of methods that we will implement, and I'll just be lazy about that implementation and do everything in the header file for fun. I think at least. That's my goal, right? Maybe not. No, yeah, I'll put some things. Never mind. I'll put some things in the implementation file, but maybe not for HTree node stuff. So HTree node stuff we'll do there, and that's going to be like the base class. It's called a Huffman tree node, HTree node. And then there's going to be subclasses of that. There's going to be the leaf kind, right? The one that represents characters and frequencies, and then like the internal node kind that represents frequencies and children, right? So we need those. That's a thing. And yeah, that will like the internal nodes, you know that they have like what they need to hold on to is left and right stuff. And the leaf nodes, they need to hold on to the character and the character's frequency. Those are the new things. I guess they always have frequency, right? That can be the shared thing between the two subclasses. Like this has a frequency, this has a frequency. We can share that in the base class. But the character stuff, that's part of a leaf form. The left and right stuff, that's part of an internal node. See that? See the difference? So we can use inheritance to deal with that and keep track of that. That's wonderful. And that will be HTree node stuff. And then the actual compression with the priority queue and things, that's in huffmancoding.cpp. And by the way, all of the stuff is from our textbook. We can go stare at the textbook as well as we're implementing that. But yeah, I'll show that to you. Eventually, what you're going to implement, what you're going to turn in is just the CPP file. So I'm going to be lazy and do a lot in the header file. You'll just put that there, but that's not part of what you're turning in. All right. You still need it to get the tests to pass on your own end for the rest of it, though. All right. So yeah, that is my my present to you. We're going to do it together. And so this slide is kind of saying a little bit of that. So there's two kinds of nodes. Like I said, leaves and internal nodes. Every leaf has a character and a frequency. We know that. Every internal node has a left and right child pointer and a frequency. So the frequency is the shared thing that we can put in the base class. That'll be a thing. I'll show you that the destructor for internal nodes needs to be recursive because like this all is all going to be on the heap. And if you want to destruct an internal node like this, if you want to destruct this leaf, you better recursively destruct these guys, right? Destruct the rest of the tree. That's your left and your right. So essentially that's a recursive problem, isn't it? Recursive deletion. Crazy. So there's that. What else? What else? I'll show that to you in a second. And then at that point, when you say delete, because delete calls a destructor on a heap thing, where I mean, or for heap, I mean the dynamic memory location, not the data structure this time. So when you say delete on something that was made on the heap, that's what hands off the problem to the destructor before the memory gets reclaimed for that one thing. So you just say delete on the root. If we do this right, it will delete the whole tree for us. That's wonderful. So, all right, today we're going to do Huffman HTree node stuff, and then next time we'll do the rest. So that'll be on Tuesday. So let's start. So huffmancoding.h. And then the way you run all of this, if you want to do it ahead of time, there is a main file. So I've given you here. You've got a make file. In the make file, you've got compress. There's a program called compress that kind of runs all your stuff. It takes a file, you give it in arguments. You run the compress program with a file name, and then you either say codes second or compress. And the first one gives you like the actual codes for each character, and then compress like actually compresses the file. And I've done that for us using the things that we've done. So like the file we want to build the Huffman tree with is in the first argument, argv1. was it codes or compress was argv2. I build the tree by giving the file to our Huffman coding class. It's going to be part of the constructor. And then if we get the codes, we can print them out in this way. Otherwise, there's a compress method that does the compression on the actual characters of the file to like print out ones and zeros just for fun. We're not going to do binary conversion. We'll just print out a string of ones and zeros to make it easy on ourselves. So yeah, try to figure out how compress works. It's in the write-up. Things that you could do. But I've made a little makefile command that just like runs a bunch of tests for the compression to see if it works. So compress makefile run compress tests, like runs some things with Shakespeare. So like I've given you the entire text of Shakespeare, and I've given you like a file with just the word with every the sentence with every letter of the alphabet in it. Quick brown fox jumps over the lazy dog. And so this will generate some things, and you can compare the output if you save it with this operation, right? You can save it and get back a file, and you can compare it with this. This is the output that you should see when you run that run compressed text stuff. Okay, so that's the actual thing that should happen, and I think we'll go from there. So all I care about is to do today the H-tree nodes stuff. Are you ready for that? I'll show you the inheritance hierarchy. We'll see how it works. And then that will be the first piece of your lab. Yay. So, okay. Every Huffman tree node, this is the base class. This is the base class. Every node should have, what do they share, right? Put all the shared stuff up there. If I want to interact with anything in the tree, like I'm not sure if I'm going to interact with it through this base class, because I'm not sure if I have a leaf or another internal node to the left and to the right of an internal node. So I'm going to put a bunch of things up here, all right? So we know we've got leaf nodes and internal nodes. So here's the base class. Here's a leaf node class that inherits from the base class. And then here's an internal node class that inherits from the base class. I hope that hierarchy makes sense to us. That's that. And then, yeah, the goal is eventually to store this whole tree from the perspective of the base class, because I'm not sure if at the root I just have a character or if I have other things. So like down here, there's a Huffman coding class that actually does compression. It's got the compress method and all that. And so we're going to have the root of our tree and every other like node in our tree. We're gonna store it from the perspective of the base class. It's gonna be H tree node star. So whatever we want to do to a tree better exist in the base class. It has to be there if we're going to use it that way. All right. So yeah, so we're going to use inheritance. We have leaf node and internal node. And every time we say H tree node star, this will be the abstract class. So we know that if we have like a concrete pointer to a node, it's either going to be really a leaf node or really an internal node. All right. And the way that we'll tell the difference is kind of like we were doing in the slides the other day. We'll make an isLeaf member function. Virtual, of course, right? We'll have an isLeaf member function where in the internal node class, it will continue to return false, but in the leaf node class, we'll override this to return true. And that's how we will know if our H tree node star really was a leaf or not. Does that make sense? That's how that'll work. And then every H tree node, no matter if it's a leaf node or a internal node, it's going to have a frequency. And so we're going to put the frequency up in the base class because they're going to share that. So int frequency is a member variable. It is protected, as you know we need now. Okay. We need that. And then any other way we want to interact with the tree needs to be in the base class because we're going to treat everything in the tree like an H tree node star. All right. So we'll use the isLeaf to know if we can go left or go right. We need a getter for the frequency. We'll never change the frequency, so we don't need a setter. When we make the tree node, we'll give it the frequency we want it to have, though. So there's a getter for the frequency, a virtual method for whether or not it's a leaf. And yeah, we can, once we get the result of isLeaf back from our H tree node star, either it was the false, we are a leaf, or sorry, false, we are not a leaf, or true, if we overrode this in the leaf class, like we really were a leaf, we know if this returns true, we can't go left or right. We know if it doesn't return true, we can go left or right. All right? That's how that works. So that's the process. And so we'll need a destructor. Like I was saying, we're going to need a virtual destructor if we're dealing with memory, and we will be. That's going to be unfortunate, but necessary. So we're going to need a virtual destructor in the base class to make sure that we get the real destructor called for whatever internal node or leaf node we were trying to destruct at the time, because otherwise it would run this default one, which has nothing to delete. All right, so we'd leak memory if that was not virtual, if that was not getting the actual version of the most specific base class, or sorry, subclass. Yeah, that's how that works. And we are going to get frequency return something is leaf will just default to false. We'll override that in the leaf case. And then sometimes, like depending on if it was a leaf, right? We're gonna have this is our window into the tree. Like if it was a leaf, we can call get character, and it will return something normal. Yeah, because leaves hold characters. This is how we'll get the character out of a leaf if isLeaf gave us back true. We're going to interact with the tree through H-tree node stars. So we need operations for getting characters, going left and going right, and knowing if we're a leaf or not. We have to put that all here so I can interact with the tree from the perspective of the base class. All right? All these operations need to exist. I will override them as necessary. In the leaf class, we'll override get character, right? To actually give back the character we're saving in the leaf node. For go left and go right, if it wasn't a leaf, I will override get left and get right to actually give back H-tree node stars that represent the left subtree and the right subtree. But here are default implementations of all of those. I should not be using them if I was the wrong kind of node. And I'll know which kind of node I am by calling isLeaf. Does that make sense? That's how that's going to work. So, yeah. And you know that we need inheritance because we have these different kinds of nodes. We have to treat everybody like the base class because think about our priority queue. We start out with a bunch of leaves, and then we start making internal nodes too, don't we? And so what is the type of our priority queue? We are forced to use inheritance, right? We have to say priority queue of something, and it's got to be only one type. So we have to treat our nodes like the base class because of that. Like when we're building the tree itself, we're going to start with a priority queue. If I can spell priority queue. Why are you like that, PowerPoint? Priority queue of, we can't just say internal node, we can't just say leaf node, because we have sometimes one, sometimes the other. We have to say H-tree node star here. Does that make sense? That's going to give us the ability to put both kinds of nodes in our priority queues, because we need to be able to put leaves, we need to be able to put internal nodes as well, as we combine leaves, yeah? So we have to use inheritance. You could, of course, cheat and just make an H-tree node star type that had a frequency as well as a left and a right and a character. Just like remember which one to not use if like the left and right were null or something. But this is cleaner, I think. It's a good example of inheritance. It's better this way. So yeah, we put all the things that we could ever want to do to a tree node in H-tree node, the base class. And this base class is an abstract base class because we're going to give it a virtual destructor, but we're not going to give the destructor an implementation. And by not doing that, that creates a pure virtual method. And that means that H-tree node, the class, we can never make an object of type H-tree node. We can never make a concrete H-tree node. Impossible. Because of that. We have to subclass it and give it everybody a destructor, which is honestly what we needed because sometimes we have heap memory involved. All right? So yeah, we will override the rest of this. We're going to interact with the tree from the perspective of H-tree node. So we need to be able to go left, go right, get a character, and know if we're a leaf or not, to know which of these we can actually call, all right? And the shared thing goes in the base class as usual. That's the frequency, all right? Does that make enough sense so far? There's a lot going on. And so there's that. That's the first piece. And for a weird reason, when you say equals 0 on a destructor, it's very weird. In Huffman coding.cpp, just a quirk of the C++ language, you actually have to give a body for the destructor, even though it's pure virtual and we said it didn't exist for the destructor of H-tree nodes. It's really weird. This line, like when I say equals default, that's just like a cool kid's way of saying no body, nothing, do nothing at all. But that's what the cool kids tend to say, so I want you to see that at least once. And yeah, so I have to say that for no good reason. I have no, I'm going to complain. Sorry. Where were we? Here. So yeah, for a weird reason, for a destructor, only when you're doing a pure virtual destructor, you have to give it a body, give it an empty body in the implementation file. It's dumb. It's very dumb. I'm sorry. But with that, everything else is fine. And so that's the H-tree node class itself. That's the base class. We're going to interact with the tree through that. We have the ability to do everything we could possibly want to do. We can always go left or go right if we need to combine nodes, because we're going to need to do that as we're building priority queues, right? To like construct something, like once we've made it, like we need to get out the left and get out the right when we're traversing it. Things like that need to happen. And we got the frequency saved, all right? Are we ready for leaf nodes and internal nodes? Because leaf nodes are inheriting, and their new thing is the character that's part of every leaf node, right? That's what they're always holding on to in addition to the frequency that we're inheriting. Every leaf node has a character that's actually there, and every internal node, you better believe it has a real left and right pointer. 2 H-tree node stars, because to the left of me could be a leaf. It could also be another internal node. You see that? It's got to be from the base class's perspective there. Okay? So that's how that works. And yeah, we're pretty much ready to do everything. We'll do the destructor last, but let's think about this from the leaf node's perspective. We're going to see it as an H-tree node star. For a leaf node, we need to mark that it really was a leaf node, so we need to override as leaf, don't we? For the leaf node class, we need to override as leaf to say, yes, it was a leaf, actually. True. Okay? That needs to happen. The constructor for leaf nodes, you need to give it the frequency and the character. We'll use the base class's constructor to put in the frequency, and then the character we can set ourselves. That's our member variable. And now the is leaf, let's override that. When we say is leaf, will return true. And it's already marked as virtual in the base class. You don't say virtual ever again, but it's good practice to say override here, because you'll get an error if you forgot to say virtual once you say override. So that's great. So we want to say true. Every leaf really is a leaf. Yeah. Does that implementation make enough sense so far? It's important. And then the getter for the character, we actually have a character in our leaf nodes. So if we ever say get character here, don't just return some dummy value. Actually return the character that we're saving. We have one. So I'm, again, just going to be lazy and do this in the implementation, or in the header, in the declaration part of this, but that's fine. Const override. And we will return our actual character. That is our member variable, just right there. There it is. Does that implementation make sense? Every leaf node is an H-tree node. It gets the frequency for free from the H-tree node base class. You build it with the frequency and a character. Use the base class's constructor to put in the frequency, and then fill in the character, your member variable, just using initializer lists as usual. Override the get character and the isLeaf methods of the base class, because we really do have a character return. Here's how you do it, and it's that one. And then we really are a leaf, so say true now, so that whoever calls that on us knows that they can call get character right afterward. Okay, so that's a leaf node. That's the simplest one, simpler of the two, I would say. Does that make sense? Questions about that one? And then the destructor for a leaf node, there's nothing to do because there's nothing on the heap. This character is going to go away. This frequency was also just an int. It's going to go away with the object. There's nothing that was on the heap or anything that we needed to take care of to delete ourselves. Okay? That is a destructor that is all done with. Are we ready for internal node? That's the leaf node implementation. And then for internal nodes, they are also H-tree node stars. They have a frequency. We get the frequency. But they also have lefts and rights. Every internal node needs to be able to go left and right and get another tree, another subtree. Could be a leaf, could be an internal node. We don't know. So our lefts and our rights are going to be H-tree node stars. All right? And that's where they're going to be. And we're going to assume that they were made on the heap as well. Okay? So internal nodes, they store a frequency. We'll use, like when you construct an internal node, you give me the left, the right, and the frequency. We'll use the base class as usual to construct the frequency part. And then the left and right, we'll just add ourselves. And then when we're an internal node, the default implementation of isLeaf is good for us. We are indeed not a leaf. That's fine. That's good to keep that there. But we do have a left and right that are real, that we've set. So these getters, get left and get right, we need to override and actually give back our lefts and rights. Does that make sense? We got to do that. That is important. So these getters no longer useless to us. We will do this. Get left const override. get right const override. We have a left and right pointers. We've called them left and right. There they are. There's that one. There's that one. We have a handle onto them now. Okay? That's how that works. And that's more or less it. The destructor is the last piece of the puzzle. It needs to be recursive in a sense. And it will just kind of be automatic, the fact that it's recursive, but let me show you. So first of all, you know that, let's see, how do I want to say this? Yeah, are we ready for the destructor, by the way? The very first step is going to be, well, knowing what happens when destruction occurs. Like how does destruction occur in the first place? So here's our tree. You're going to be interacting with this tree. If you want to get rid of it and not leak memory, right? You're going to be interacting with this tree. All the nodes have been made on the heap, right? The root of your tree for any useful Huffman tree is going to be an internal node, right? There's a root node. It's going to be an internal node, and so it has a left and a right. Okay? If you said delete root and didn't give a destructor implementation, it would just delete that node itself off the heap. We know this, right? That's how destruction works. That was the single object. You said delete root. The destructor was empty. It had no body. And so it's going to forget about the left and right that were also on the heap. Yes? So delete root would just, all delete root is ever going to do, unless you say otherwise, it's of course going to delete the object itself. But anything else it's holding on to that also needed to go away, you better do something about it in the destructor's implementation. All right? So what you want to have happen in the destructor is, dun, 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 you would like to delete your left subtree. Yeah? Recursively. Just have it go away, please. And then same with the right subtree. Get rid of that. And the beauty of this is the way you call a destructor is not normal. You don't say like left.destruct yourself, right.destruct yourself. The way that you delete things, the way that you get rid of things, is you say delete. Yeah? Delete calls the destructor for you if there is one. And so what you're going to do, what we'll end up doing is we will say our left subtree, this is like if we went left, we say left to get there. This is our left. This is our right. All right? This whole thing is called left. This whole thing is called right, that subtree, a pointer to it. If we want to get rid of this, we can believe in the magic of recursion right now. We can say delete left. Because, do you see how that's going to be recursive if we implement our destructor like this? Because again, this will be getting at another internal node, and it itself will say delete my left, delete my right. Do you see how that's going to work out? It's just going to be all down the line, just like that. Delete left would call the destructor on this smaller node, which we're going to assume has been implemented correctly to get rid of that entire tree. Magic of recursion. Then we say delete right. Semicolon. That calls the destructor for you. Whenever you say delete on something that was on the heap, that calls the destructor for us. So that's wonderful. Calls the destructor. Come on, PowerPoint. Why are you deleting older things before newer things? Calls destructor, that's an R for you. Yay. That's wonderful. And so when you say delete right, you can just assume that that got deleted. And then delete root whenever, like that one was always going to go away at the end anyway. So essentially, the moral of the story is for internal nodes, to delete those things, you just say delete left to recursively delete the left subtree, delete right to recursively delete the right subtree. You yourself are already being, it's in the process, you're in the process of being destructed, so you yourself are going to go away at the very end of the destructor anyway. You've done everything at that point. So the body of the destructor for internal nodes is just you say delete left, delete right. That's the moral of this story. Does that make a little bit of sense? It's as if you're saying, I don't know, dot destruct on left and dot destruct on right, if you want to think about it that way. It's just the way the destructor gets called is you say delete on heap things. That's how it goes away. And so, yeah. Dun, dun, dun. It will end up being recursive because of that. All of our H3 nodes are going to be made on the heap, so we got to get rid of them. So it's tilde internal node, and then parentheses, of course, what do we got to do? Delete our left, get rid of everything on the left of us, recursively delete right. If left was just a leaf, it was still made on the heap, it'll go away, that's fine. If left was an internal node, we'll again hit this implementation for that leaf, or for that internal node, right? And it itself will delete its left first, and then it's right before we delete it itself. That's just the process. So you do a destructor call, the object itself is the very last thing to go away. It's like you call the destructor, it runs the code to delete this thing, and then the object itself is going to go away at the end of all that, after it's finished. And that, I think, is every different way I could explain it. I hope that made enough sense. So that's destructor stuff. Yeah, you can just say, so now, the whole idea is we can just say delete on the root of the tree. That will delete the whole tree for us, because the destructors were implemented correctly. All right? Because they were implemented correctly, we are good to go. And yeah, I think that's everything for H tree node stuff. Dun, dun, dun. So yeah, that's that. Internal nodes, leaf nodes. We've got implementations for everything, overridden properly. If I save this, is something going to happen? Probably not. Can I say make to compile anything? It's probably got some empty stuff. Yeah, just things that I have not actually given. These are linker errors, and that's what we want. So we're good, I think. So yeah, that. And there's nothing else extra to implement in the base class, right? Let me just make sure. So yeah, that's the first part of it. I implemented it all in huffmancoding.h, which is actually not what you're turning in. So you're going to get that implementation for free when you turn stuff in. But if you want to test the rest, you got to have that there. So yeah, I hope it made a little bit of sense. It was a good excuse to use inheritance. And so this is just a really good combination of everything we've learned. Like, we're combining data structures, we're using fancy object-oriented stuff, and that is the start of your lab. So I do highly encourage you to try and do the rest yourself. But I think, yeah, when we come back on Tuesday, I'll do it for you as well. And yeah, that will be the last of it. That will be the last of it. You do have to take care, if you want to implement it and get the same score as me, the same ones and zeros, you do have to add one thing to the left and one thing to the right. Like the order in which you make those subtrees have to be the same as my implementation. So that's, if you get the wrong answer, maybe swap those if you try it ahead of time. But I think that's all that I want to do for the day. Are we good? Any questions about any of that? Yeah. Oh, no, we're good to say not over it. I don't actually know. I've never thought about it that way. The reason I don't immediately jump to saying override is because the name is different now. Like, this is leaf node, it's not tilde H tree node. I wonder. I honestly don't know. Let's search for that. That's a really good question. For a virtual destructor in C++, do you say override on the base, on the subclasses, destructors? I really don't know. Dun, dun, dun. The base class destructor is virtual. The destructors of all derived classes are automatically virtual. Yeah, I guess this thing I've somehow ingrained in my mind and I can't fully explain it. The core guidelines explicitly recommend against declaring derived class destructors virtual or override if the base class destructor is already virtual. The reasoning is that destructors don't truly override in the same way that other virtual functions do, as they always do each other. They always chain themselves in a weird way. So that's why we don't say override. I don't think it matters. Can we do it? Is the question. But yeah, apparently the C++ people themselves say that you shouldn't be doing this because destructors are weird in a weird way. But I think you can, because it was virtual. The destructor was virtual in the base class. I still get the same errors. But yeah, for a weird reason, just due to a quirk of how destructors work, we don't say override for those only. That's so weird, and I'd have to learn more about it. Yeah, it's just a matter of style, I think. I'll have to read the core guidelines just to know the difference, but that's interesting in itself. Yeah. Other questions? I hope that made enough sense. But yeah, that's just like a quirk that you learn one day. Destructors we don't say override for some weird reason. All right. Yeah, I think that's all that I wanted to say for the day as far as the lecture goes, and also the lab. Are we ready to talk about the final? Well, let's do that. So we have, we're in week 15, so there's 2 more weeks of actual class, right? Next week, we have a holiday on Thursday. We got Thanksgiving, so we'll only have the Tuesday class. And then week 17 is the last week of classes. We'll review for the final. And then week 18 is finals week. You just take the final on the final day, and that's it. You never come back. So I will release the final info page and the extra credit assignment page, as it's one last test. And then eventually I'll release the actual final exam right there, as we did for our midterms. So yeah, let's look at both of these. Okay, we have a final time. This is when I read it off the schedule. Please double check me. I think that's when it should be. That's when I put it on the syllabus at least. The final will be on the Tuesday of finals week, 12/9, December 9th. Boop. Get it out of the way. The second day of finals week. It'll be at the same time as class time, but we only get an hour and 15 minutes in this room. Hour and 50, I mean. Hour and 50 minutes in this room. Less than our normal class time, because it's just we take the final and we leave. So it's technically a longer final than longer test than the midterms, but yeah, it's only an hour and 50 minutes that we last in this room for. So there's that. Here are the topics for the final. I'm going to try to hit a little bit harder the stuff that I haven't tested you on, but you know that everything builds on top of itself in this class. You should see everything. You should expect to see everything. So for midterm 1 and midterm 2, and here are new things. Huffman compression is like the last major topic. I might say a little bit more due to the weird, what was it? It was Veterans Day falling on a Tuesday this year. We lost a lecture, and so Huffman compression is honestly the last real thing we're going to cover anyway. But yeah, if I say a little bit more, you can still expect really easy topics, easy questions on anything after Huffman compression, okay? If I say a little bit more on Tuesday about something else, I promise not to test you too hard on that thing. But yeah, those are things you should be ready for. I will not be testing you on any chapters of the book that I had you read that I never mentioned in class. So balanced tree stuff, AVL trees, red-black trees, graphs, those things are important for a future class. You will see them again. I'm not going to deal with those in this class. All right? You've seen them once now, and so in theory, life is going to be smooth sailing for you when you get to them in a future class. But I will not deal with them in CSCI 41. All right. So yeah, that would be evil anyway if we didn't have a lecture on it. So yeah, those are the topics. That's when it is, and the format is exactly as the midterms have been. You know exactly what to expect now. You're going to have some questions that you can maybe fill in the blank, or just like you write code the entirety of the code. And the rules are exactly the same. Closed book, you can have your cheat sheet. That's a printer paper size. You handwrite it on the front and the back. You can use both sides, and that's it. You can have scratch paper, of course, but that's all you get. No, like you're on the Canvas page only, taking the test. Can't go to any other tabs. Go get on the server, use a calculator, anything else, okay? So yeah, here is a sample final from last time I taught the class, and I think that's everything I wanted to say about it. You know when it's going to be, what's going to be on it, and what to expect. Any questions about any of that? We're almost to the end. So close. And then, yeah, with every test, our last test, comes the last extra credit assignment. This one's for the big bucks. This is worth up to 5% extra credit if you want to do it. Remember that no late submissions are allowed for extra credit, so make sure to not wait until the last minute to upload it, because I won't give you credit if it's late. All right. So the test comes out on the 9th. So the midnight of the 8th, 11:59 p.m. is when the extra credit will be due for everyone, regardless of if you have extensions. No extensions for tests or extra credit. So it's due for everybody the day before the test comes out at midnight, 11:59. Okay? So the rules are exactly the same as always. If you would like, you can make a review video going over some stuff that might appear on the exam. So like go look at the topics list and come up with some fun examples and you'll post it here, and it's like an excuse for you to study, and your peers will get some extra studying out of it too. It is a win-win, and that is why I like this assignment for you. Yeah, just as usual, go over a bunch of examples, make up some stuff for topics that might appear on the exam, right? Don't just like go over midterm 1 things or something. That is not, while that technically might appear on the exam, that is not good enough. You should have done that for the midterm 1 extra credit assignment. Go over harder things that we've covered more recently, okay? And then, yeah, just like pretend to give a little mini lecture maybe, to like go over the things, draw pictures, write code, whatever you need to do to get your point across, because you're giving a review of stuff. So if you want a quarter of the extra credit, make a 10-minute video going over like 1 problem or 2 small problems that you came up with or something. If you want half of the extra credit, please make at least a 20-minute video going over a few things, maybe like a more involved example that you fill out as you go through it. And if you want the full 5%, you're going to make like almost a lecture's worth of content. You're going to make at least a 40-minute video, please, where you can just like record your screen or something using this kind of software. It's called OBS is the one that I use. If you'd like, I can help you with that. And then just, yeah, I like to say at the end, just like make sure you're making something new. You gotta do extra stuff to get extra credit, right? You gotta make new code, write new slides, draw new diagrams. Can't just go over your textbook. Can't just go over my slides that I worked hard on. Can't just go over a lab that you've already completed that was part of your grade. Make something brand new, please, okay? And ask me if you have any questions about whether your idea is good enough. Usually, if you make something and I can tell that you worked hard on it, I'll give you the credit, okay? So yeah, I'm happy to help. If you have any questions about any of this, if you're not sure how to record yourself, there are ways. It's not too hard. And yeah, if you'd like to do it, please take advantage of it. That's our extra credit opportunity, the last one of the semester. Any questions about that? Yes. Ooh. Thank you, Caitlin. Yes, you want that, right? So please respond to that. Get Caitlin paid. All right, so I think that's everything. I think that's all that I wanted to say about the final. You got the lab out if you want to try that earlier than when I do it for you. And then on the day of the final, the Tuesday of finals week, you'll come in here. This will be available. You'll take the test. Then that's it. We're almost there. We're so close. So I think that is all that I wanted to say for the day. I will stop the recording.